Okay, welcome back, everyone. Let's get started. People who are online, you can hear me, right? Okay, thank you, Sean. Okay, so today is lecture 22, and today we are like shifting gears a little bit because we're not discussing about any new model. We are not discussing about any new techniques in machine learning and AI, but rather we're talking about of like a fairly active research area that's bias and fairness in AI systems. And there is a lot of emphasis on this topic right now, and we'll see why. Obviously, it's a vast topic and not everything can be covered, but I'll try to uh, like discuss a little bit about from where does this come into our systems and some of the ways of mitigating this, some of the ways of dealing with it. And another important aspect of any AI pipeline or machine learning pipeline as such, and when I say pipeline, I mean right from the data collection stage to the evaluation stage, that entire pipeline, there's something that's known as interpretability. And you will see that term, of course, like in some of the recent papers more than the ones that were published like 10 years ago. And the reason being that like now we understand like neural networks, we understand deep learning models. And you've seen that the way they work is more like a black box approach. I mean, I know that like I'm computing, like I'm updating the weights, I'm calculating the gradients, and then I'm making some predictions about the parameters, right? But if you ask me, and let's say there is a deep model, and if you ask me to explain why I got this result versus the other, then it's hard for me to say like this parameter resulted in this, right? And then just by looking at the data also, that's almost impossible because we have like these huge data sets. So this issue of interpretability has come in because many businesses feel reluctant to adopt these approaches. For example, like in medicine or like in banking system. Specifically in medicine, because like the practitioners want to know why I should be recommending this to a patient versus something else. So those are some of the important, I think, issues that uh, that are there with any machine learning pipeline, with any AI pipeline, and so we need to discuss those. And so that's the topic for today. I'll begin with a little bit of motivation. I don't know if you're familiar with this Apple credit card issue or not. So this was something that was there in the news in like late 2019. You might or might not have come across that. So what's happening was that people found out, and this started with a tweet, and many people were like complaining that there was this gender bias in the way Apple was issuing their like credit card limits. And like despite being like everything being equal for men and women, men were getting higher like credit card limits as compared to like their female spouse. And even when like they like the female the spouse had a larger income or credit score. So this like really came into light in like late 2019, and the allegations that like people were making for like Apple was that the algorithm was making credit decisions for Apple, and it was biased because it was giving greater credit limit to men as compared to women, and so there's like clearly a gender bias. And more importantly, people who implemented this algorithm were not like able to completely explain why this was happening and how the algorithm worked. And that goes back to the interpretation part of like any ML or AI algorithm. And you can see that there is clearly a gender bias introduced into the system, and we don't know like how to deal with this, right? And so this was like a huge issue that, as I said, started with a tweet, and then even like Apple's co-founder and their spouse were like a part of that entire like allegation tweet that went on. But it was like this actually point. This is like the tip of the iceberg. This points to an important issue that's there, and why this algorithm is predicting something like different for different genders, despite like everything being equal. So there is definitely some bias out there that's implicit maybe, but that exists. Okay, so this is like one example, and here's a source to this article that you can just like go ahead and read the details of this and if something has been done or not. So as I said, like men with bad credit scores and irregular income were getting better offers than women. And this is clearly like a gender bias that's introduced in the algorithm itself. Um, there is another like very prevalent bias that's there in computer algorithms, specifically vision algorithms. So gender and racial bias in image recognition is something that's very well known and has been there, specifically when we think about these pre-trained models or transfer learning. So you've seen these and you've used in one of your assignments, a pre-trained model. And obviously, a pre-trained model is based on some existing data set, right? So it was trained on some existing data set. And if it has a bias, then that's even more dangerous because I will be using that like model for some other applications, for some other prediction. So I need to know why this is happening and how this is happening. So in this paper, like I have the link to the source, you can go and check. ImageNet was found to have like this racial, gender, and intersectional bias. And what was found was like these were embedded in not just like this one, but the models that were built on ImageNet. Now, obviously, this goes back to the fact that like the way the data was created, the data set was created, the way the data was collected, because your model is as good as your data, right? And so it seems that like using this transfer, and I think we discussed a little bit of this when we were talking about word embeddings, right? So the same issue like exists in computer vision algorithms because I have this pre-trained model and I'm using it to do some prediction. And then when the data itself is biased, then you can imagine the quality of my predictions, right? So the things that were found in these two models, so OpenAI's IGPT and Google's SimCLR v2, both are built or trained on ImageNet. And it was found that like both of them had, and obviously these have like already annotated images, so they have like labeled data, and then you have to like train on that. And there were like racial prejudices, there were gender biases, and for example, when they were trying to find like cluster certain words, so there was a huge gender bias in the way like male and business and office came together, and then family and female and children came together. So those kind of biases were there. And there was like this sentiment analysis that was done using these, and there was a lot of stereotyping that was found. For example, embeddings from IGPT, the OpenAI IGPT, and this like Google's SimCLR v2, they exhibited bias for Arab Muslims because they were benchmarking like pleasant versus. So basically, they were trying to find some kind like categorize images like pleasant and unpleasant, and there was this like specific category of like people coming from a particular race that were like categorized as like being in the unpleasant category. So that like that level and like very disturbing trend, but that existed when they were like trying to figure out what kind of biases exist in this one. And like IGPT obviously was trained on ImageNet. So ImageNet obviously is biased. That's why we're getting such results. And similarly, like both of these models, they associated white people more with like tools associated with like working and all, and Black people with weapons. So that's again like a huge disturbing trend. And you can read the entire paper here. So both these models were found to have, and this is serious, right? Because if I use this data set to predict, let's say for like some security app, or maybe like on an airport or something, then I'm just like flagging certain like people from certain, and this has been found in a lot of studies that like people from certain race and certain gender and certain ethnicities, they get more flagged on airports as compared to others. And so that's like bad, right? Like even as we model and as we create our own models, we don't want that bias to seep through our pipeline in any ways, right? Because we are like not helping the society in any way, rather we are just like doing disservice in some ways, right? So that's like a bias in computer vision algorithms. And of course, ImageNet is the source. And then we discussed a little bit about bias in word embeddings, if you remember. So word embeddings were created by using these like huge data sets. And so these are also pre-trained models, and I can just like pick that up and use it. And we have discussed a lot of that when we were discussing language models. So I won't go a lot into the detail of that. I don't know if you remember this example when these existing models were used to find some association between words in different languages. It was always found that like if I have some association from man is to computer programmer, woman is to homemaker. So that was the kind of bias that's there. And so these word embeddings obviously cannot be used as such to make certain predictions because they already have this inherent bias and we need to do something about this. right? And obviously, as you can tell, like all these three examples, the Apple credit card issue, and then the bias in computer vision algorithms, and then the bias in word embeddings, that the primary source is the data itself. And I would rather say the primary source is the society itself, because my data is like coming from, for example, the language is coming from like the language that we use. The language data is coming from there, right? And so in some ways, like we need to take care of that, and we need to account for that when we are building our models. And so there are certain ways, and as I said, this is a pretty active area of research where we are trying to de-bias our algorithms, we are trying to de-bias our data and make like a more fair sort of place where like we can have, I would say, free from prejudice type algorithms and models. Okay. So as we just saw in these three examples, and that was like a motivation of like why we need to de-bias our algorithms and our models, because bias can exist in like all shapes and forms. These are just like three examples. If you just go to Google Scholar and search for papers that point to bias in machine learning models, this is not something new. Like bias has always existed, even when we were not using machine learning, but rather statistical learning. And so there are ways to deal with it, but it seems we haven't done enough. Specifically when, like with deep learning, we haven't done enough. We need to do more. Because first of all, with deep learning, there is this idea of like, we cannot interpret the model as well. And so we cannot really figure from where is this bias seeping into my model, right? And so as I said, bias can be introduced. So what we just like saw in bias in word embeddings and bias in like computer vision algorithms is the bias that seeped into my ML pipeline from the data stage itself, right? So maybe I did not have a representative, a good representation of like the entire population or language or something that introduced bias in my model. But then bias can be introduced anywhere throughout the pipeline. It can be in the way the algorithm is designed, because remember, like most of the algorithms, they look for majority class, and then like we're looking at accuracy, right, in most of the models. So if I am predicting all the majority class, then I'm like accurate. So then that's like some kind of an algorithmic bias. So it can be introduced anywhere, and so we have to be extra careful where it came from, then only we'll be able to address it. Okay, so what is fairness? Well, again, you will find multiple definitions of bias and fairness in literature. So I didn't exactly come up with a definition here, because it depends. It depends on like what issue in the model or what issue in the data you're trying to address. So again, we have like at a fundamental level, bias is like, just remember that bias is present, and if we are like in some ways overrepresenting or underrepresenting a particular class or a category, then maybe we've introduced bias. And of course, like you have to define it depending on like what exactly you're like the problem you're trying to solve. And fairness obviously is defined for models and algorithms, and if your model is free or like almost free from any kind of prejudice or preferences for a particular race or an individual or a group, then most likely it's fair, right? So that's uh, like a high level definition. Of course, if you read the papers, and I have pointed you to two important papers, if you read the papers, you will see that like there are specific definitions that are given to bias and fairness. But regardless, we understand the high level idea, right? What bias is. Okay, so having like said what bias is and some of the important examples of bias in machine learning models and AI models, there are different types of biases, and broadly, like I've tried to classify them into data-driven and interpretation-driven. However, again, I would like point that out. If you read papers, you will see that different authors try to categorize them into different categories, but we'll try to cover as much as we can, and like I'll try to cover some of the mitigation strategies as well. But it's beyond like the scope of this lecture to cover everything. But you should definitely go and read some of the recent papers that are out there for like dealing with bias and fairness in AI, because I think that's an important aspect of any machine learning model, which we don't actually cover we didn't cover in any of our projects, right? We just like go and create and do some prediction and then evaluate. But I think if you're solving a real world problem, that's something that you should always keep in mind when training your models, when building your models and doing evaluation, right? So maybe it can be data driven. As I said, that like it started from the point when the data was collected and the way the data was treated and the way we actually created our model. And then it could be interpretation driven, meaning how do we interpret things? For example, one very common example of interpretation driven is correlation versus causation. Like we found that these two variables are correlated, but not necessarily that was the cause of the correlation. So making sure that if we have uncovered such a relationship in the data, we understand it. And that's why interpretation is so important, because maybe the cause of a particular trend or a particular correlation wasn't a result of the variable that we are looking at, right? So that's like interpretation driven. Sometimes we like to overgeneralize things that can be dangerous. So for example, I have a small data set and I made some observations and some predictions using that data set. And then, and maybe I collected the data set, let's say like I live here, right, in Troy. So I just collected a data set here and then I'm making the interpretation for the entire country or maybe the entire world. That could be like an overgeneralization because my sample is not really a representative of like the entire world population, right? So those kind of things. And you will see that overgeneralization in a lot of research papers as well. So being careful like when reading such papers, because that result is not representing the entire world, right? So that's something that's interpretation driven. And automation, AI generated decisions favored over human generated decisions. So that's the thing about interpretation and interpretability in machine learning models. And as I said, like initially, that this is an important research area because we want like some very accurate decisions. And we have seen that with neural networks, with AI, we are getting really good quality predictions, right? But then at what cost? Like, do we really understand why we are predicting this? For example, if you go back to this one, bias in computer vision algorithms, like OpenAI's IGPT is like a well-known, very well-performing model, but this is what it was doing, right? It was giving like more positive to people with a lighter skin. So is that something that we want, like at the cost of accuracy, right? So that's what this thing is, right? And of course, this is like a very active research area where we are trying to find interpretability versus, or rather explainability versus how accurate the model is, right? So accuracy versus explainability, like which one is important? And again, this is somewhat similar to like, I would say bias variance trade-off. Like this is a trade-off in itself, whether I'm able to explain the model and how accurate my model is. Because if you think about like, let's say decision trees, I can specifically tell you that this point was my threshold. And based on that, I segregated the data. Like I can literally give you why my algorithm did this, right? And even like with support vector machines, I am coming with a hyperplane that's separating the data. So I can give you the exact points. This is where the data is being separated and this is why. But I cannot really tell you in a deep network, this is why I got this prediction because this value was this much. So this is more like a black box. And so, of course, I'm using it for a lot of problems because they're giving me better accuracy, better approximation. But then we have to see at what cost. Because, for example, for application in medicine, a doctor would definitely like to know why we are predicting this for this particular patient, because then they can put that patient into a particular like group and then maybe give them different medication, right? So that's something that they cannot just go ahead and do until they understand why it predicted this thing, right? So that's what this is, interpretation driven. And then going back to data driven, which is more common and has been there ever since statistical learning was there. So the first one is selection bias, meaning data selection has some kind of imbalance. Data selection itself had class imbalance. For example, if we go back to this ImageNet data set, we cannot like 100% accuse ImageNet of like everything, because the way this data was collected, it's more like in the in North, like the input images are coming from North America and European countries, and so that they have a larger representation of lighter skin and less representation of like people from other regions. And so that's there, right? The way you collected the data has this issue already. So that's what the selection bias is. And selection bias has this important issue that's known as class imbalance, right? Class imbalance is there in medical data as well. For example, we are trying to predict like cancer or not. And so the number of people who actually had cancer, like the labeled data, that class is pretty low, right? So that class imbalance exists in the data. But the point here is that we should know before using the data set that this huge class imbalance exists, and then prescribe solutions according to that. Or even like fraud detection data sets. They have a huge class imbalance. Like very few fraudulent cases come up as compared to people who are like the usual regular customers, right? So it has to the data that you're using as an input should reflect randomization as well, in addition to like this issue of class imbalance, right? So it should be randomized. That's another thing. If it's not randomized, if you're like making selections based on some like input bias, then you already biased your selection process. Okay, so that's one. The other is sampling bias, meaning let's say I already have some data, but the way and the issue actually this of sampling bias is somewhat related to selection bias, because let's say I already have a data set that has some majority class, and I'm sampling from that. So the likelihood of selecting the majority class is more, and then I'm using that as an input to my model, right? So that's what sampling bias is. Some data instances are more frequently sampled because maybe the data was distributed like that. And so I'm like more frequently sampling the ones that are more frequent, or the frequent class or the majority class in my data, right? And then reporting bias, that has happened a lot in some of the research areas where data shared did not reflect the actual likelihood. The experiments were in some ways biased, and so that resulted in a reporting bias, right? So there are a lot of papers. In fact, this came up in one of the conferences a few years ago, where when they tried to reconstruct a lot of experiments from certain papers, they never got the same result. So that was a reporting bias, because the way they had reported in the paper wasn't like exactly matching to what they were trying to predict or what they were trying to report. Right? So there, like that bias came in. So I wouldn't name the conference. Like if you just Google, you'll know where that happened. So that's that. Okay, so let's actually discuss. Any questions so far? This is pretty straightforward until now, right? So yeah, and here, let me see. Okay. Okay, so here I just tried to list different forms of selection bias. As I said, like sometimes selection bias and sampling bias, they like go together, and one could be a result of the other. So sometimes we can say that selection bias is like introduced during data collection stage, because the way I selected like the individuals or the groups or the data for analysis wasn't randomized, and so it did not achieve what it wanted to achieve. And there could be different types of selection bias. One is sampling bias, and some of the examples of sampling bias are like non-randomized selection. You're doing some pre-screening of individuals, so you already introduce some kind of bias. Let's say I'm like collecting data for some medical task, and I'm already doing some kind of pre-screening of people, and I'm not like randomly picking individuals from some given population. And so because I pre-screened the trial participants based on something, that would bias my selection, right? Because I explicitly introduced that bias in my system. And so I'm not like, so I cannot like make a universal approximation for something. Maybe I should mention that in my study that my results would be biased based on this selection. That is fair, but like making an approximation for some universal fact is not, right? Okay, discounting trials, subjects, and these things actually happen a lot in like medicine. You'll see a lot of papers out there that actually point to these kind of biases. Discounting trials, subjects tests that did not run to completion. So sometimes you're running an experiment and you just like came up with the conclusion and the results somewhere in between, although the experiment had to run for a longer period of time, and you did not run it for that period of time. You just collected data in between somewhere, and maybe you could have like gotten different values for the other observations that you did not actually observe. right? So again, a lot of this happens in medicine and also in like physical sciences. You're observing a phenomena or something, and you do not wait enough, and so that could seep in with like the bias. Migration bias, like people moving in and out of the area, they were not accounted for. When you started a study, and let's say the study had to last for a couple of years, you do not account for people who are moving in and out, because that should also be part of your data. And then length time bias, very like I would say much related to how and for what length of time you are like collecting data, especially for medicine purposes. And so length time bias gets introduced there. And like time interval, early termination of a trial, again, very similar to like when we said, I think discounting trials, very similar to that. But you are doing an early termination of a trial when the results support the desired calculation, because you wanted some kind of a result to come out. But like maybe later on that result wouldn't, the data wouldn't support your result. And so you just stopped the trial somewhere in between. Okay, so data partitioning or dividing data with some knowledge of the contents and then using that data accordingly. So again, like you're explicitly introducing a bias in your data. And this is important because, as I said, a lot of studies actually performed in different areas of like research. I wouldn't say like especially physical sciences, performing repeated experiments and reporting only the most favorable results is bias, right? So if you performed a lot of experiments, you should be reporting the unfavorable ones as well, because this leads to a general like wrong idea of a particular like experiment or a particular phenomena, right? So all of these are examples of selection bias, and there are different types of selection bias. Let's focus on one thing, and that's like pretty common in machine learning models. That's class imbalance, and it's a part of our data-related or data-driven bias, which is class imbalance. And we know like class imbalance occurs in a lot of data sets. I just said like in medicine, in banking type areas, and like the positive class sometimes occurs with a reduced frequency, and that like um, makes this imbalance result like give us results that are not quite what we would like to have, right? So for example, if you have a classifier and you have like this majority class that's higher in number, and then like some minority class, and then you're just like checking for accuracy. And if you like 100%, if your classifier 100% classifies the positive class, that's the majority class, better you say that it's a very good classifier, right? So class imbalance can like lead to a lot of issues that, and obviously imbalance can be dangerous for like a medical like application, medical diagnosis, because we just like discarded the minority class, which was actually the one which we were interested in, right? Because I was really interested in figuring out if a person is susceptible to getting cancer or not, rather than people who are not. And so that's going to like adversely affect my model and my prediction and the usage of my model. And so obviously this is a very important issue amongst all the issues, amongst all the data-driven issues that we were just like figured. And so obviously there are methods to deal with this. And this is the most common issue that you will also come across even while solving any machine learning or AI problem yourself, getting publicly available data sets. So how to deal with that? And so there are different methods to address this class imbalance. And the first one is this data level methods. And I would say this is something that I've used a lot myself, specifically when working with recommender systems data, and we're trying to predict people who are going to buy something or not if we show them an ad, because there are very few clicks as compared to people browsing. So that's a very like highly imbalanced data set. I mean, you would have noticed when browsing on the internet, you hardly click on an ad. So the clicks are like very low in number as compared to people browsing. That's an imbalanced data set, and we need to do something about it, because like my classifier is going to predict the majority, and I would never be able to get the right kind of output that I need. Okay. So data level methods of addressing a class imbalance, they include oversampling and undersampling. So there are two things I can do. I can just like split my data set into like my positive and negative class or like whatever majority and minority class. And either I can oversample from the minority class or I can undersample from my majority class, right? So in that sense, I can create some kind of a balance so that I have like equal number of majority and minority. And then I can use that to train my model. So before training, this is like the pre-processing step. Now, one very widely used technique for oversampling is known as SMOTE, and that's like synthetic minority oversampling technique. You can go and read the details of like how this is done, or maybe you've come across that in any statistics class. And then what it does is it produces this artificial minority samples by interpolating between existing minorities. So there is this range of values that exist in the minority class, right? So I can just like go ahead and create synthetic data points within that range of values, right? And you can give some inputs of like how many values need to be created. And obviously it uses some predetermined distribution. And so you're like, it's more like you're creating some sampling distribution and you're picking values from that. And you shouldn't go beyond that range. So that's the constraint, I would say. And so in this scenario, like in the customer data that I was talking about, I can oversample from people who were, or I can create like these artificial samples for people who were like clicking, but similar but different. And so I can create a balance between the minority and the majority. And then I'll have a balance, and so my model won't be biased towards like one of them. So that's one SMOTE. And another technique is batch selection, in which we can pick batches of data that have like a balanced class ratio. So basically what we do is we restrict like the number of positive data points that we can pick, and it shouldn't go beyond a certain ratio, right? So the class imbalance should be like 1:99 or something. It should be like within this range of like 1:5 or something like that. So that creates a pretty good balance or a good mix. And then because we're doing like batch picking, so in every batch, I need to have at least, let's say, 2 from the minority and 3 from the majority, because I decided 2:3. So that kind of a ratio can be maintained, and that would lead to my classifier not like under predicting or over predicting any of those. Okay, so these are like data level methods. That means I'm doing something with the data, and there are more. If you're interested, I can point you to a lot of papers. You can just go to Google Scholar and also like just check data level methods for class imbalance, and you can get like a lot of, you can read a lot of papers. But I would say these papers are pretty, like most of them would be before 2010 or something. A lot of work had been done in that during that time in this area, and this was more like related to statistical learning. Of course, we use it for machine learning as well. Okay, and then there are like algorithmic level methods. These are more common now with AI models. And what we do is, unlike these data sampling methods, we handle this like we don't change our data. We don't change our data, we keep the data as it is. But in some ways, we do some kind of adjustment to like my data points so that the likelihood of my algorithm picking up the minority class is more than the majority class, right? So I'm like increasing the likelihood of those points being picked. And so how do I do that? Well, I can do some kind of weight adjustment. So maybe I added some weight to my minority class, and in some ways adjusted the likelihood of my algorithm picking those more because they have a higher weight, so they have a higher likelihood of being picked up, and my algorithm is going to pick those more than my minority class, right? So then reweighing, that's something that can be done. And instead, like the learning of the decision process is adjusted in a way that increases the importance of the one that was like less in number. Okay. So some of the algorithms, I think there is another class of algorithm that actually puts a penalty on the majority class sometimes. So it's either like you add a weight to the minority class or you add a penalty to the minority class. So a lot of algorithms are there that can actually change the likelihood or maybe add some weight to the likelihood of picking the minority class more than the majority class. Okay. And then there is this like recent way or like a more recent, I would say, algorithm. These are like cost sensitive algorithms that are imposing penalties through some cost matrix. So you're increasing the cost of the minority group. And in some ways, it's like So we are decreasing the likelihood that the model will incorrectly classify instances from this group. Right? So this is a more complex way of thinking about it, because I'm actually incorporating that in my model itself. It's not in the data, it's not in the sampling step, but it's rather in my model itself. Right? Okay, so this was like, these are some of the ways of like, how can we deal with class imbalance when we have like some class imbalance in my data, right? But there are biases that are there in my features themselves. So how do I deal with that? So what exactly does that mean? Okay. For example, in facial recognition, we just saw what happened with ImageNet, right? So there can be some latent biases within the data, meaning that, as I said, we collected that data from somewhere. And so let's say I collected the data more like in North America and Europe as compared to other countries or other continents. And so obviously there is a larger number of people with a particular skin color and a particular hair color and eye color and so on, right? So there is that bias that's there in the data set. And it's in some ways a latent bias, because I have some unequal representation of different like racial groups or maybe gender for whatever reason. Maybe like, and it's not very easy, like just to give you an idea of like, because you might be thinking, why are we using ImageNet? Right? So think about like collecting images and then annotating them, labeling them. It's a lot of like, if there's a cost involved with that, right? And so that's the whole point of using like transfer. Like you and I can just sit at home and we can just like train new models on the pre-trained models. That's the whole point of using these pre-trained, because I don't want to go out and like collect new pictures and then do some classification task, right? And so there is a cost involved with that. And we need a way to deal with this implicit bias or this latent bias that exists in these existing like data sets, right? So for example, in facial recognition, this bias can be problematic because you will have like, for example, in law enforcement, errors could lead to false accusations and arrests, right? It could be that dangerous. And so we need to do something about it. And there are ways to deal with that, like these latent biases. There's some like more recent work done in this area where you have like the models adjusted or models built in such a way that they can figure out these biases and mitigate them or reduce them. Okay, so let's see how we can address these. Okay, what is this coming up? Let me close it. Okay, so we saw that with class imbalance, when I was doing smooth, that means like oversampling or undersampling, I am like physically going and doing something with the data, right? Now, what we want now with like these deep learning models and these larger models is that my model, in some ways, can my like model uncover these biases the moment like we feed in the data? And if yes, then can the model itself help mitigate those biases? And a quick answer to that question is yes. This is a very active area of research in deep learning, and it can be divided into two major like areas, I would say. The first one is bias mitigation, and the second one is inclusion. So again, let me repeat what I'm trying to do here, because you must be wondering that we already did a lot with the class imbalance problem in my data set. But what we want to do is we don't want to like do oversampling or undersampling. If there is a bias, my model should be able to figure that out and do some adjustment while learning, so that when we get some kind of prediction, it's the prediction is not biased in some ways, right? So maybe my model can learn that this is biased and then do something about it, right? So that's what we are trying to do with these two strategies. So the first one is bias mitigation. So given some biased model or data, we remove that problematic signal, because there is some feature that's seeping through. For example, if you think about the Apple credit card problem, there is that bias based on gender, that like men are getting higher credit, like higher credit approval and higher credit limit as compared to women, right? So there is this like gender as a feature that's creating that problematic signal. And so we can do something about that particular signal or that particular feature and maybe mitigate the output, right? And so maybe I can predict this, like whether to give somebody a credit card or not, based on everything else except gender. or maybe reduce the impact of that gender, right? So that's what like bias mitigation strategies do. Okay. And then there is this like inclusion. So instead of like removing the signal, what we can do is there are other important signals. For example, again, going back to the credit card problem, there are other important signals like your income, your level of education. So these are all positive things that should help us decide whether to give somebody a credit card or not. So maybe feeding in a higher value of these features as compared to the gender, right? And so like we can weigh these features in some ways, like, right? So that like some features are more important than the others, right? And so we can come up with like a more fair model or more fair outcome. All right. So bias and fairness in like a supervised classifier type of model is that like we can create a classifier that if the decision, first of all, like let me explain what like a biased classifier is, right? So mathematically speaking, a classifier is biased if its decision changes after being exposed to some sensitive input feature. So basically what I'm saying is it's like, for example, mathematically speaking, let's say I have a classifier, right? So obviously a function, and there is a feature z, and my classifier f of x is fair with respect to z if this like this like with respect to z, my prediction just does not change, right? So my classifier is not biased then. If because of like, let's say if I have my input, let's say I have a classifier that is classifying based on like some input features, and I add this input feature z, but it does not change the outcome drastically, right? So then it can be considered as not biased, right? So mathematically speaking, this is how many of the recent papers have defined unbiased classifier as, right? So very high level, like if there is some additional sensitive input feature, which most likely is causing some kind of bias, for example, gender in the credit card problem, and the outcome does not change, then my classifier is not biased, right? Okay, in other words, like I can say that if I'm basing my definition of my classifier based on the single variable, single attribute, then maybe in some ways I would think about the likelihood of getting the outcome as 1. Let's say I have some likelihood of getting 1 or 0, right? 1 meaning give the credit card, 0 meaning don't give, right? Or maybe like this is a threshold or something. So the likelihood of getting a 1 as an outcome does not change whether z has a value 0 or a 1, right? Then it can be considered as not biased. Again, let me repeat, like the likelihood of getting a 1, whether my z, let's say my z can take 2 values like 0 and 1, right? And my classifier has some likelihood of giving out a 1 or a 0, right? So let's say my classifier had like some likelihood of getting a 1 given some y and given some z, right? And so let's say this z is 1 here. Z also has like 0 and 1 values, right? So the likelihood does not change when I change like this. If my z takes a value 0, the likelihood of getting a 1 is still the same. So then it's an unbiased classifier, right? So this is the definition of like, this is one of the definitions of an unbiased classifier. So having said that, evaluation, bias, and fairness. So there are different ways of like evaluating these classifiers. So one is disaggregated evaluation, the other is intersectional evaluation. There's this like paper 1 that talks more about these two. So I wouldn't go into a lot of details of these two types of evaluation, but rather I would jump to 2 different models that are being used recently to deal with this bias. So now we understand what like an unbiased classifier looks like, right? And so based on that, what we can do is we can create these 2 different types of models that can help us deal with these biases, right? So the first one is this adversarial multitask learning to mitigate bias. And the way this model works, and I don't know why I forgot to put the link to the paper. Okay, I'll do that after the lecture. So there is a paper that talks about this technique. So I just picked up these two techniques because they are pretty interesting, and they're using deep learning models to deal with this bias problem. So what is done in this one high level is, for example, I have some input X. Okay, so I have some input X, and I feed this into a deep learning model. It could be like multiple layers, right? And maybe I'm doing some kind of prediction. So the problem here that I'm trying to solve was to predict some output. So this is my target, right? But in addition to that, what I do is I make my network also predict some values for like every time I predict a Y, I also want to predict that Z. And I figured that my Z is, so basically what I'm doing is a joint prediction of Z and Y in some ways, right? So how is this helpful? Like, how does that help? So what I'll do is I have like two predictions, two outcomes, and I already knew that this Z, let's say maybe this Z was the gender feature in my credit card problem. I already knew that this is the one that's problematic, right? And if I wasn't like outputting this in a normal neural network setup, I would have calculated the gradient of the loss with respect to all the parameters and then back propagated, right? But even if I have like two outcomes, for example, Z and Y, I would still use back propagation to calculate the gradients, do back propagation, update the gradients, and so on. So what I can do, like the whole point of outputting this Z as a predicted value, as opposed to the actual input that I'm getting, is that I can compute like some gradients for this one as well and back propagate, that I can negate the gradient for this particular feature. So meaning when this one like is back propagated, I don't like, I'll restrict the back propagation for this one, right? So then what will happen is this will, in a subsequent like iterations, it's going to reduce the impact of Z on my overall decision. That's the high level. Yeah, question. Yes, exactly. Yeah, yeah. Yeah. So it's like in some ways removing those correlations. And then because it's done in subsequent steps, maybe I'm not like 100% like removing that variable, but I am like reducing the impact of that in some way. Predicted. Yes. Yes, exactly. Yeah. That's a good point actually. Because like let's say I don't have that as an input, but I could still like estimate it in some ways and then de-bias it. The de-bias is a good word actually. Yeah. So we can de-bias this. Yeah. So this particular technique of jointly predicting the target and the problematic signal actually is known as adversarial multitask learning, and this helps us mitigate bias in the sense that, like in every subsequent iteration, this is in some ways a confounding variable, and I figured that this is a confounding variable, and I reduced the impact of that and the interaction of this with other variables as well, because this was a confounding variable. Okay. Now, this looks like a good solution. The only issue with this solution is that in the credit card problem, I knew that this gender is an issue because like many customers like found out that this gender is causing an issue. And so I decided that this is the problematic signal. And so let me just like go and reduce it. But in many of the data sets, I don't specifically know that this is the problematic signal, right? In many of the complex data sets, I might never know what is the problematic signal that's causing this bias. So, and in fact, even for the credit card problem, it could have been something else in addition to this that is causing the issue, right? So what should I do about it? And so there is another technique that actually builds on this one in some ways. And it uses like variational autoencoders, if you remember from one of our previous lectures. And this is known as adaptive resampling for automated debiasing. And there's like this paper here from which I extracted this model. And this is a very interesting model because what we do here is that we create like the variational autoencoder structure, and then we estimate, we don't use the data as it is, but we try to estimate the values of the variables. And obviously when you construct it, so I don't know if you remember the structure or not. So in variational autoencoders, we have like the encoder-decoder architecture where we had like some kind of latent distribution of the latent variables, right? So it learned from the input data X, and that then it encoded into some distribution that's a latent distribution. And so why this is latent? Because like I don't know what all features it's going to learn. Because based on my encoding, it's going to come up with some features, which is good. And then I'm going to reconstruct the output based on that, right? So the encoder-decoder architecture, instead of like exactly predicting the attributes or the features, I'm creating some kind of distribution of those, right? So how is this helpful in like debiasing what like I'm doing? So from this latent distribution of like different variables, like whatever it learned from the data, right? What I can do is I can estimate the distribution of these like variables once again, right? So if I get some kind of a distribution like this, right? There are certain attributes that are overrepresented and there are certain attributes that are underrepresented, right? So what I can do is like, for example, faces of certain skin color are overrepresented, certain skin colors are underrepresented. So if my data distribution is something like this and I have like some overrepresentation or overrepresented data somewhere here and underrepresented somewhere here, then obviously the likelihood of me selecting this one is higher, right? Because that's how my data is distributed. But in the reconstruction stage, what I can do is I can explicitly diminish or reduce the likelihood of these latent variables being selected versus these, right? Because I can like engineer in some ways these like latent variables. Like I will see that there is an overrepresentation of this distribution that I estimated from the input, right? But because I know that there is an overestimation because of some inherent or like intrinsic bias, I would select less of these overrepresented ones and more of the underrepresented ones, and then train my model. Or then reconstruct the output, right? I can do that. So basically what we do is like we redefine the likelihood probability in some ways that it's like inversely related to where my variables lie in this distribution that I just estimated using the encoder, right? So this is a very interesting and like excellent results with this paper. Let me quickly go to this. I hope, yeah, this one here. So what they found was like, okay, this is the results. I wanted to see the, yeah, so initially what was found was like in the larger data set and the one like ImageNet, we are familiar with that one. So whenever they were sampling from that data set, there was a larger like representation of a particular skin color and people from a particular race and so on, versus these type of images that had like people from different skin colors and like maybe they were wearing glasses or hats and things like that, right? So they were introducing some kind of bias. But then when we are trying to apply this to some like application, let's say I'm trying to predict like let's say an airport security or something, right? So I have a different application there. I don't want that I get like an overrepresentation of some particular race versus the other. And so for that, I can use this like variational encoder type architecture, wherein I can figure out these are the ones that are overrepresented versus these are the underrepresented ones. And so when I recreate or when I like decode the input distribution, I'm going to decode in such a way that the likelihood of me selecting these and these are somehow leveled, right? And so very good results for actually, so methodology, actually, I'll show you quickly. Yes, so they have a variational autoencoder, VAE type structure here, right? And then within this like latent, like this part within the encoder-decoder architecture, this one here, when we have the estimated features or like the estimated Z, you should like what we're doing is we are updating positive debiasing probability, right? So we are making like explicitly making the likelihood of selecting the underrepresented like data points greater in some ways than the ones that are like overrepresented, right? So that's like update positive debiasing probabilities. And the results of this model were like really good, because I can quickly show you. Okay. Okay, so what this was like, obviously this model was doing was sampling probabilities over the training set. And then this is like the top 10 faces with the lowest resampling probability. Now you can see the input had like these type of faces as the majority, but now these are amongst the lowest, because that's how I updated the likelihood of like when I'm sampling. And these are the top 10 faces with highest resampling probability. Resampling meaning once I have like recreated the data set, and then like I'm sampling from that, and then I'm like using that as an input to another model. So as you can see, like this is a good result in terms of like the balance that is creating, because there are a very few of these different types of images as compared to these. And so obviously it is creating a good balance there. Okay. Yeah, and so like here they're discussing the performance as compared to the other ones, and then they're like they've also pointed like the different categories of people and how the like what the accuracy was for them, because it has been a universal fact that like most of the prediction models, they don't work well for dark, male, female type input images, and so this model obtained a very good like outcome in terms of that. All right, this is a paper that's worth reading. I would definitely recommend everybody to go and read this one. Okay, as usual, my computer is out of charge. I don't know, it gets like discharged pretty quickly. Okay, so then the last part of today's lecture is interpretability in AI models. And as I said initially, this is also a very important aspect of any machine learning model. And in fact, this has been the biggest hindrance of the adoption of these models to many industries and many application areas like medicine, and then like even the finance sector, where they're still using like some basic ML models as opposed to deep learning models, despite their like very good accuracy and very good performance. Okay. So of course, like different papers describe interpretability in like different ways, but it's basically the ability to understand and reason about the model output, right? So if I'm getting a particular prediction, I should be able to explain why I'm getting this versus why I'm not getting the other outcome, right? And so, as I said, in order to have a larger adoption of these models in business and medicine, transparency is required. These like deep learning or like deep networks, they are like black boxes, because there is so much of non-linearity that we keep adding with every subsequent layer that it's hard to describe how the variables got updated and why the variables got updated, and then how I came up with this particular prediction, right? And so model transparency has been defined in terms of like 3 parameters. So simulability, whether a human can use this input together and with the model to reproduce every calculation. For example, with a decision tree, I can, right? I can just like go ahead and like, maybe it'll take a long time, but I can literally by hand do all the calculations and say that this is how the splits happened. And this is why I'm here at a particular branch in my decision tree. But like, I cannot do that with a neural network. Like I cannot go and simulate the entire process by hand and say that these were the values throughout the network, and this is why I'm predicting this, right? So that's an important aspect of interpretability. And until unless like humans understand the changes in model parameters, it's hard to explain, right? It's difficult to explain, and it's difficult to convince anyone to adopt this model to be implemented in a real world application. So that's one. And then decomposability, whether there's an intuitive explanation for all the model parameters. Well, I would say in most of the deep learning models, that's like next to impossible. So decomposability is low. And then algorithmic transparency, which again is an ability to explain the working of the learning process of the algorithm. Of course, like high level, I can describe that, okay, gradient descent is there, gradient descent is learning, this is the way the learning process is happening. But I cannot for sure say why, like, even if you think about the loss function as such, it's hard to describe where exactly were these model parameters, and so that this resulted in my decision, right? Because these will be used as aids to a larger decision process. And so until and unless there is like high level of like explainability, we cannot really implement these. For example, I'll like give you a quick example in recommender systems. For example, uh, deep learning models have been used and they've been found to be pretty effective. But then there is a lower requirement of like this transparency in recommender systems. I mean, of course, I recommended a user, maybe their level of satisfaction was low. But first of all, level of satisfaction is a subjective, I would say, issue. I don't have a proper definition of like what is your level of satisfaction versus mine. Maybe I can come up with some like vague idea of that. But then the cost involved in recommender systems when like predicting and showing people certain items, and then maybe they didn't like that item. So the cost involved is lower as compared to the cost involved in like medicine and banking applications, right? So we have to be more careful, and this totally depends. Like the adoption of these models totally depends on like what application you're using them in. Right? So as I said, in recommender systems, it's pretty easy. But even there is like this whole alternate area of research where people are using models like discrete choice models, for example, right? So in discrete choice models, you can literally say, these are the input factors, and this is why I'm getting this probability. And so I can literally go and do it by hand and say that this is why the probability of somebody selecting a particular item is higher. And so maybe I should use this model versus like a deep learning model for a recommendation, right? So there are alternates there. And like last but not the least, in some of the applications, for example, these advertising type applications or even recommender systems, there is a huge amount of data, and like every second we are changing things. And so maybe like there is like this need of faster models that have the ability to work with huge amount of data. And so, yeah, it's a good application for deep learning models, right? Because they are faster, like better processing and everything. And so excellent. But in medicine, we don't need that, right? And so we need, like there is this other side of machine learning that we need, which is like a better explainability prediction, of course, but then you don't have that humongous amount of data as well. So basically we have to, as like machine learning practitioners or people who are building these models, we have to make sure that we are recommending a solution based on its application, and not just like because deep learning models are good at prediction and these are like universal approximators, so like they are not good for every application. So that's the whole point, right? And so that's what interpretability in AI models is. Now, and of course, like I have two readings for you. You should like go over these papers that talk about these issues in greater detail and point to some other papers. Again, like before we end this lecture, this is an ongoing area of research, specifically with the like deep learning models, with the embeddings and the pre-trained models that we are using. So that's something that you should keep in mind whenever like designing an ML pipeline or a data science project or anything like that. Right? All right, so that's all I had for today. Any questions before we end? Okay, that's fine. So let me stop recording. Thank you so much for joining, everyone. That's all I have.